Hello, everyone, and welcome to another Flint and Walling virtual training event. My name is Dan Painter. I am the Product Training and Development Manager at Flint and Walling, and I will be hosting today's web conference. Today's topic and title is Submersible Pump and Motor Troubleshooting. Through a couple graphics up on the screen that I have to confess is an opinion, but I think this opinion is probably shared quite a bit throughout the water well industry. I think most water well contractors would agree with the statement. In today's business and today's world and climate, very, very little repairs are done, and I get that because when we look at the price of replacement parts and then throw labor on top of all that, sometimes that can get a little costly when maybe just offering up a brand new submersible pump and motor assembly with a brand new warranty is the way to go. So anyway, the fact that these pumps are not necessarily repaired does not negate the fact that we ought to make sure that we have some pretty good troubleshooting skills so that we don't find ourselves replacing a pump only to find that the problem that we had initially is still the same problem. And so with that, let's go ahead and get started. When I look at pumps, and whether they're submersibles, which is what we're going to be talking about today, or whether they're jet pumps or centrifugal pumps, really, I mean, any type of pump that we manufacture, I always look at it, we call these submersible pumps, but I think if we look at it today from a troubleshooting perspective, we might be better off referring to these as submersible pump and motor assemblies. In other words, I look at it as two entirely separate components that come together and make up, as we've already said, a submersible pump and motor assembly. Of course, there's the hydraulic side of this assembly, which is the pump end, and some people will also refer to this as the wet end of the pump. But within that pump end is going to be a series of impellers and diffusers, and this is the portion of the pump that's going to, let's say, have the responsibility of all the hydraulics, okay? So moving water, pressurizing it, so on and so forth. On the bottom side, of course, is the electric side of this assembly, and that's your motor down there. And so when troubleshooting, when I'm attempting to make attempt at troubleshooting, I look at the pump and motor assembly this way. And the questions that I might ask initially, and I'm going to run through a few of these scenarios today, but a few questions that I would ask, I'm asking those questions to provide me with some direction. In other words, am I going to be looking more at the hydraulic side of this, or is it going to be more motor related? And again, those are the questions that I'll ask early on. So, with that said, when it comes to troubleshooting, it makes sense to look at a pump and motor assembly as two separate components. You've got the hydraulics, or the pump end, on the top side. You've got the electrical, the motor, on the bottom side. So if we look at the pump end, the pump's going to have a hex shaft with a coupling on the end of it. And this is fairly generic. I mean, if you take submersible pumps, if you break the pump and motor apart, you're going to see exactly what I'm talking about here. There is, again, a hex stainless steel shaft that's got a pressed coupling. You can see it is splined. And then that wheel made up with the shaft that comes off the motor, better said, the rotor. And as again, you can see on the right-hand side of your screen. So that's, this is where the marriage takes place, really, between the pump and the motor assembly. This is where the two, in so many words, tend to become one, right? It's right there at that assembly. But that assembly is very, very important. We'll talk about it as we go. But I'm going to pull my highlighter up here. I can just tell you from a manufacturing standpoint, Flint and Walling spends a lot of time, or I should say a lot of attention to detail. Again, we manufacture these components at our Kendallville facility, and when we cut these splines on this shaft as well as in the coupling itself, there's science there. You cannot be too deep or too shallow. You cannot be too tight or too loose. Otherwise, something catastrophic will happen. If you're not mating these two components together properly there. But again, that's just an area where the two come together. And so let's go ahead and start talking about some actual troubleshooting. When I'm in classroom, I oftentimes ask this question. I look out over the contractors that are out there, and I'll say, let me ask a question. How many customer calls that you get regarding a pump problem or whatever starts off like this? I don't have any water. Oftentimes, that's about the only thing you have to go by. The homeowner has no idea what's going on. They simply call you up and they say, hey, I don't have any water. Or you might hear something like this, I don't have any water pressure. My water pressure is really, really low. You might hear a comment like that. I'll tell you this much, at least in my experience, and particularly with homeowners, all right, consumers. I'm talking about lay people. They think water pressure is flow rate. And they think the more pressure they have, the more water flow they have, which, any of us in this industry know that that's not the case. The more pressure, typically the less flow, and so on and so forth. But again, these are questions that are pretty vague, or comments, I should say, that are pretty vague. What they end up doing is they cause you and I to somewhat go on what I would call a reconnaissance mission. When I define that, I would say that we have to ask questions. We have to either directly or indirectly. It doesn't matter how we get this information, but we've got to collect some information so that we can figure out what we need to do to fix the problem. Okay, so again, I start off by asking some very, very fundamental questions. They say, I don't have any water. That's what they say. And so, again, I'm going to try to figure out, is this a hydraulic problem or is this maybe a motor problem? And so the question that I will ask is very simple. Is the pump running? Is the pump running? That's a pretty close-ended question. And we got two choices there, yes or no, right? If the customer responds back and says, no, the pump is not running, all right? Now let's think about this for a second. The pump is not running, which might be a good reason why they don't have any water, right? But what runs the pump? Well, it's the motor, right? It's the motor side of that. And so by asking that very fundamental question there, and I'm not saying I'm going to stay on this path, but it gets me headed down a path that I'm going to try to determine whether this is a motor issue or whether it's a pump end issue. And so when they tell me that the pump is not running, my mind at least is going to start focusing on, okay, well, maybe there's an issue with the motor, maybe there's issue with power to the motor, whatever, but it's going to land more on that motor side, more so than on the hydraulic side. All right, so what if they say yes? The pump is running. All right. All right. Well, if they say the pump's running, it tells me the motor's running, right? I mean, again, these are some very upfront, very, very basic fundamental questions. It tells me the motor's running. So if they say that the pump is running, here comes my next question. Does the pump shut off? There's, again, two choices there, right? So if they say the pump is running and I ask them, does the pump shut off? If their response is yes, all right, now let's stop and think about this just for a second. They called, they said they had very little water, they don't have any water. They tell me that the pump is running, and they tell me that the pump is shutting off, meaning it is building up at least enough pressure to satisfy the pressure switch and shut off. So, when I look at that, I'm thinking, okay, the motor seems to be functioning fine, but obviously the pump's running and it's shutting off, and this customer still has an issue, right? They still have an issue. So what I'm going to start looking at in this case is I'm going to start looking at the hydraulic side of this issue, all right? I got to figure out why is the pump running and it's shutting off but not producing the water flow or pressure that the customer is wanting. All right, so I would kind of look at that on the hydraulic side. Before we go down this path too much further, I want to throw another one up here. What if their response was no? Is the pump running? Yes. Is it shutting off? No, it's sitting there and it's just running all the time, right? It's just running all the time. So we're going to look at a few basic scenarios here, okay? So, and I guess we'll just start off with this. The pump is running, but the pump is not shutting off, okay? It's not shutting off. And now again, you see my little gray arrow over there? I'm kind of moving back to this electrical side again, and I'll explain that in the next slide. But the pump's running, tells me that the motor's running, but it's not shutting off. So let's look at what could be some of the issues here. So the pump operates properly, but won't shut off, all right? So this is going to be little scenario number one. It operates properly, but it won't shut off, all right? Well, one of the first things I'm going to look at is the pressure switch, right? That's what turns the pump on and off, just like a light switch on a wall. These pressure switches operate off of about a 20-pound pressure differential, meaning from the moment that they cut on, the pressure that they cut on at, typically it's 20 pounds higher that they'll cut off. So if you have a switch that comes on at 30 psi, more than likely that switch is designed to cut off at 50 psi. Well, that's what this switch is supposed to do. It's supposed to shut the pump off, right? It's supposed to shut the pump off. Now, in order for it to shut the pump off, the pump has to build the pressure. But there are times that the pump builds plenty of pressure and it still won't shut off. And the reason behind that is these contacts right here. You've got a set of contacts up here I've got a highlighter hovering over that area right now. But there's a set of contacts or points on both sides of this pressure switch that make and break, again, as the pump is powered on and powered off. Yeah, if those contacts are welded, you know, I've had back in the day, I've had guys tell me, yeah, we'd clean those up, we'd, you know, file them back and whatever. Again, you can do what you want. We got to make the contacts open and close. Probably the best way for that to happen is just pull that switch off there and replace it. At least that's an opinion or an attitude I have about that particular switch. As a Band-Aid, perhaps, if the pump won't shut off, I can put a hex-headed nut driver on the large spring-loaded tower where my cursor is hovering over. If you take that hex nut that's on the top of that tower and you start to loosen that up, okay, you're turning it counterclockwise, you're taking tension off of that spring. What that ultimately is going to do is it's going to lower both your on and off pressures simultaneously. So the key here is that we're lowering the off pressure, all right? And you can continue to turn that and, you know, perhaps the pump then shuts off. It just can't shut off at the 50 or 55 or 60 pounds that the switch was set at, but you may be able to get it to shut off at a lower PSI. All right, and sometimes that's going to be an indication of a pump that is, you know, it's quite a ways along in its life cycle, and it's starting to lose some performance, and a lot of that times is in the pressure that it can generate. And so again, I don't know that this would be a long-term solution, but lowering the pressure on the pressure switch may very well get that pump to shut off at least. And then we can make some decisions after that. They say, hey, we don't like this pressure that it's at now. It's like, well, then now we've got a choice to make. You want to have higher pressure? We're going to have to put a pump in there capable of producing it, but the one that you have obviously is not. And so those are a couple of reasons why a pump may not shut off. Let's look at a few more reasons why that. Now this time, you know, I'm going to move off that electrical side, which was the switch, and I'm going to move back over to the hydraulic side, or at least the water, the movement of water, the pressurization of water. And so one of the things that I might be looking at is the possibility that I've got a leak or I've got a broken pipe. So when that pump's running, I'm losing a tremendous amount of water out of wherever that leak's at. All right. So, I mean, that leak can be significant enough that it simply makes it impossible for the pump to actually build up the pressure it needs to be to satisfy the pressure switch and shut it off. So if that's the case, we want to look for that. You know, whether and sometimes this leak or this broken pipe, you can look at a pressure gauge if it's properly located. You can sometimes look at a pressure gauge, and even while the pump's not running, you can start to see that pressure drop because of the leak in that drop pipe there. Another reason why a pump might shut off, might not shut off, and I talked about this just a few seconds ago, is that, you know, it's far enough along in its life cycle. You know, things are wearing out, you know, and the performance is dropping. And when we think of things wearing out inside of the pump end, the wet end, really, you've got to look at what we call our impellers and our diffusers. And I've got an image of what those look like. And in a submersible pump, you'll have several of these stacked one on top of another, right? You know, a half 10-gallon a minute submersible pump probably is going to have 8 of these in there, all right? A 1-horse 19 might have 5 or 6, but nonetheless, there's going to be a series of impellers and diffusers inside that pump that may need to be, if they're not just flat worn out, they could be clogged up. And again, we're looking at either repair or replace these things. And when we talk about replace, I'm talking about the whole pump assembly. Very few people go inside of a submersible pump end these days and do any kind of repair work at all. And most of the submersible pumps you purchase today, you couldn't get inside that wet end if you wanted to, right? I mean, if you look at them and how they're constructed, they're not threaded together anymore. The discharge is crimped in, the motor mount's crimped into the pump end, and you can't get in there unless you want to cut it apart. But nonetheless, if a pump won't shut off and there's no leak in the drop pipe and the pressure switch seems to be functioning fine, I'm going to start looking at these impellers and diffusers and just kind of make a call on whether they're either clogged with iron, with sand, debris, or if they've just flat worn out over time. The diffusers, the impeller, if you look at it here in the middle of the screen, and I'll cover this, I think, in the ensuing slide, but an impeller has 2 sides. The side here at the bottom with the large opening where my cursor is located, that's called the eye of the impeller. The top side up here, that's called the hub. So as water comes into the eye of the impeller, it's spinning, and let's look at this. These impellers are turning at the exact same rate the motor's turning. So these impellers are moving very, very rapidly inside of a submersible pump end, rapidly in the tune of about 3,450 RPMs. So those impellers, once they receive the water through that eye, they create a tremendous amount of velocity as that water is shot out of the veins along the side of that impeller. Well, all that water coming out the veins of that impeller are captured within this diffuser. And if we want to know what is the primary purpose of a diffuser, down at the bottom, it tells us that. It says the diffusers are to convert the velocity created by the impeller to pressure. And so when you have a pump that's not building pressure, obviously we probably got something going on in the impeller diffuser area of that submersible pump. Here's another one. Again, the pump's operating properly, it just won't shut off. You know, it just won't shut off. All right. So another reason for that could be a low water level. All right. A low water, where the water table has dropped. Now, we'll find this in geographic parts of the country as they go through drought conditions. We see this a lot sometimes down in the southern part of the country, Texas and the Southwest. They can get into some pretty severe drought situations. And wherever that may occur, you get a drop in the water level. All right, so when that water level drops, I'll tell you, the performance of that pump's going to fall off quickly here. So one way of again, sometimes these are just band-aids, but it gets the customer water, it gets the pump to shut off. So sometimes if it's due to a low water level or a low water table, what some contractors will do is they'll install either a gate valve or a ball valve somewhere on that discharge line, and they'll throttle that thing back. All right, they'll throttle it back, and as they throttle it back, that pump will start to build pressure. Once you get the pump throttled back to where it builds pressure and shuts off, I take the handle off that ball valve, right? I don't want anybody messing with that ball valve from this point forward, so I'd probably take the handle off of it and just leave it like it is. And again, these aren't necessarily long-term solutions, but they can buy some additional time and life out of a submersible pump before it eventually is going to have to be field scrapped. Again, we talked about this in the previous slide. I always look at this process of lowering the pressure on a pressure switch, especially if the pump was functioning fine at that setting initially, and now over years it's not. I always look at that as a band-aid, as a way of just kind of compensating for some of what's going on inside these impellers and diffusers. And you can lower that pressure switch down, and you can get that pump to cut off. While we're on the pressure switch, and before I get off of it, it's just a thought that came to me. There's a second tower on there. You'll see it in the bottom right-hand side of your screen. It's also a spring-loaded with a hex nut on top. Most of the time, that doesn't get, there's no adjustments required there, 99% of the time. So while the tall tower can raise or lower both the on-off pressure simultaneously and maintain that 20-pound differential, the lower tower there will either increase or decrease the differential. So sometimes playing around with that, you lower the tall tower down so you can get the pump to shut off. But, you could bring the bottom portion, the yaw pressure up a little bit. You might not have a 20-pound differential anymore. You might only have a 15-pound differential. But nonetheless, these are ways that we can adjust, make pressure adjustments in order to get a pump that's, again, getting old to still function for us. Let's go to this one here. It's not a situation anymore where the pump doesn't shut off. It just starts too often. I mean, every time I turn around, the daggone thing's running. Okay. Again, if you have any leaks, that leak could be in the check valve down here at the discharge of the submersible, or if you have any leak in that pipe, anything that will cause a loss of pressure, right? Cause pressure to eke out is going to start that pump up. So if it's not holding pressure and that pressure slowly creeping back, because of a leak, well, eventually when it gets to the cut-on pressure of that pressure switch, it's going to power that pump on. Pump builds up the pressure, shuts off, and the leak's still there, so the pressure starts to drop again, drop again, drop again. Eventually pump comes on, and so that could be a situation here that could be resolved by checking if there's a leak in the drop pipe, or if that check valve is actually holding down there. They'll say, hey, my pump's coming on all the time, right? That's a comment that would be, pump starts too often. That's a comment the customer may have. It just seems like that pump comes on all the time. All right. Let's talk about another reason why that may happen. The pressure tanks. Now, back in the day, these tanks were all galvanized steel, and they didn't have an air cell inside like a bladder or a bag. These were gold galvanized steel tanks, and the installer would go out there with an air compressor and pump air in the daggone thing just to give some air charge to that tank. And the problem with the galvanized steel tanks is over time, the water would absorb that air, and it would eventually lose the air charge. So if a pressure tank has either lost air and or the air charge in the pressure tank is incorrect, this is going to cause the pump to cycle. all right? So when we look at the proper air charge that should be in a pressure tank, let's look at this, okay? So the proper air charge that should be in a empty pressure tank, no water in it. I don't want any pressure on this tank. I took it off the back of the truck, okay? And before I installed it, I put an air gauge on the top air valve to check the air charge. So there's no water in this tank at all, no pressure. That air charge ought to be 2 pounds below the cut-on pressure of the pressure switch. So there would be occasions that this air charge may need to be we either add air or we have to remove air, again, depending on if you know, these pressure switch settings over here. You have a 30-50 switch, very, very popular with submersible pumps. That tank is probably going to ship out with a 28-pound air charge in it. That's where it should be. If you get out on the job and you're going to run that on up to a 40-60 switch, you want to put air in that tank, right? You're going to want to add another 10 pounds of air in that tank. Again, this air charge is critical to how a pump cycles, all right? So, you know, back in the day, and you know, I was brought up back in the day, and this is many, many, many years ago, I was told that that when a pump comes on, most people would like to see the daggone thing run for 60 seconds before it shuts off, right? That's kind of how we were taught back in the day. Let me go back to this. But if this, no, I think we're good there. Okay, so here's this next slide, and this is getting to where I was going. The pump starts and then stops almost immediately. All right, it starts and stops frequently. It's called rapid cycling. And almost every time you open a faucet, pump comes on, shut the faucet, pump shuts off. It's like, well, wait a minute, you know, why is that pump coming on and off every single time I use water? Rapid cycling of a pump is almost always due to what's called a waterlogged pressure tank. So again, back in the day with that old galvanized steel tank, once that water absorbed all that air out of there, this is exactly how that pump would start reacting. On, off, on, off, on, off, every single time water was used. So the installer would have to go out, the service tech would have to go out with his air compressor and pump more air in it. Probably have to do that, you know, a couple, 2, maybe 3 times a year just to keep air in that tank. Well, today, these tanks like we see pictured at the top of your screen are referred to as captive air tanks. And it has went a long ways towards eliminating this problem of waterlogged pressure tanks. So, but even here, you know, if we've got rubber diaphragms or we've got air cells or bags in these tanks, which act as a barrier between the air charge and the water, so that water can't absorb that air no more. If one of those diaphragms rupture, if one of those air cells or those bags rupture, over time, you're going to lose air out of that, and you're going to end up with a waterlogged tank. So again, when you hear of a pump coming on and off, on and off, on and off frequently, like it will do, more than likely, that's due to a waterlogged tank. There is another reason for this, and we're still on the hydraulic side. We're still talking about the tank side of this assembly here, the water side of it. If the pressure tank's too small, and if the pressure tank's too small, you know, if you've got I'm just throwing this out there. So it's fictitious, I hope, and to some degree. You got a 19-gallon-a-minute pump, and you've got a 5-gallon pressure tank at the top. Well, how long is it going to take that pump to fill that tank? Not very long, right? So it comes on and it shuts off. And then you use that little bit of water and it comes on and it shuts off. So again, if the tank's not waterlogged, there's a chance that the tank's undersized. It just needs to be a larger pressure tank. And maybe that, you know, pressure tank people probably ought to be the ones to do this. But as a pump manufacturer, I still think there's room in our dialogue to enforce how to properly size a pressure tank. Maybe that's going to be another web conference here in the future, because it has a whole lot to do with the wealth and welfare of a submersible pump and motor assembly. Here's the problem. The pump runs. Let's say it runs okay. It shuts off. It's just not delivering a lot of water. All right. very little water. One reason might be is that the suction screen, which is located right around the motor mount where the pump and motor come together, where that marriage takes place, there's a suction screen around there. It's typically either a plastic or stainless steel mesh screen, but if that rascal gets plugged up, this is pretty dramatic over here on the right-hand side, but if that thing gets plugged up because the water quality in that well is horrible, it's got lots and lots of iron in it, all kinds of things. And if that suction string gets plugged up, everything else north of that is going to be slowed way down, right? Barely able to pull water through there. So that might be a situation that would cause the fact that it delivers too little water. And then again, we're going back to the pump end of this thing. If it's delivering very little water, there may be something going on inside with the impellers and the diffusers. Again, these things can clog. They can wear out. The images on the screen here would be indication of a pump that was subject to some fine sand. And so, as you can see, hopefully with these images, you can see the damage that can be created by sand in a submersible well pump. So again, you start to erode material away, which is what's happening here. Your efficiencies and your performances are going to drop off shortly thereafter. So it could be worn impellers. Again, go back to these leaks. Just make sure that when the pump shuts off, it holds pressure. That it just absolutely holds pressure and doesn't have a decay in the pressure, because that would be an indication of a leak. Well, also these check valves, right? A defective check valve. And I'm talking about the check valve that is not just, anywhere along the line. If there's going to be a check valve in the discharger submersible pumps, they all have them these days. There could be some inline check valves up here, but if anything gets cross-turned, it comes apart and something gets in there cocked in a check valve, and you're trying to run water through there, it plays havoc on the efficiency of a pump when you're trying to run water through something that, is not wanting to cooperate. Pump runs but delivers no water. Now, there's a big difference between no water and little water, right? But this pump isn't delivering any water at all. All right. One possible cause is that the shaft. I'm talking about the pump shaft. You remember we had that pump shaft up here. If that thing is broke, your motor's going to run, but your pump's not going to turn, so the pump's not going to deliver any water. If this shaft coupling is worn out, again, you could have a situation where the motor's running, but it's the spline on the top of that motor is just spinning on the inside of that shaft, or that coupling there. So it's not turning the pump in. So that might be a situation. And again, with so many of these pumps that are non-repairable, some of these things that I'm talking about, the only way you would be able to determine it, you take the pump and motor apart and pull down on that coupling and see if that shaft comes right out of the assembly. If it's broken, more than likely it will. Again, going back to that suction screen, if that dang on thing gets clogged completely, which almost looks like the one on the screen is, that pump can sit in there, be running, and it's not going to deliver water because it can't receive any through that completely clogged suction screen. And again, we talked about this earlier too. If you've got a water table that drops, we get a water table that drops every time that happens. And in a lot of cases, in fact, I've had contractors tell me, they said, man, we had to go back and lower all these pumps because they weren't pumping any water. The water table had dropped so far down. And so again, these are all situations that are, that can cause these kind of issues. Just a handful of other pump end issues here. I want to throw a couple up here. Defective check valves. I'm talking about the ones in the top of the discharge of submersible pumps. I have an opinion on those. I don't like them, never have. I sold pumps back in the 70s. I sold a lot of different brands, submersibles. None of them had check valve issues because none of them had check valves. But somewhere along the way, and I know this is kind of coming across maybe a little weird for a pump guy, but anyway, they put a check valve in the discharge. And the only reason that I'm not a big fan of that is because if you ever saw the water as it's leaving that discharge, I tried to indicate this with my little swirly line there. That water is spinning at about the rate the motor's turning. It's a very turbulent environment inside that discharge. And so, again, I've looked at every pump company's instruction manuals, and they'll always say this, all of them. Sometimes they bury it in the text, but they always strongly recommend the addition of an inline check valve somewhere, either up at the tank or somewhere in the drop pipe, but add an additional check valve so that we're not solely relying on the check valve shipped in the discharge of your submersible pump and motor assembly. That'll go a long ways right there to eliminating an issue that may or may not occur down here, okay, down there. Some other pump end issues are what's called upthrust, all right, upthrust conditions. All pumps are going to be subject to this. There's nobody that's immune from being in an upthrust condition. Again, if we look at this assembly down here, this impeller has an eye. It's on the bottom. It's that large opening. The hub sits up on top, and it's on that hub where we put a thrust washer. All right, we put a thrust washer. And if you look over on the left-hand side, that pump end, we happen to use a stainless steel in our construction. But if you look over here on the left-hand side, you'll see that every one of those stages, every one of those impellers will have a stainless steel thrust washer or thrust bearing around the hub of that impeller. And the reason behind this is right here, all right? When you drop a pump in the well for the very first time, I don't care if it's a new installation or you're replacing a pump, more than likely, everything from the static water level inside the well, everything from that to the top is all open, right? The pressure tank doesn't have any water in it. The water line feeding the pressure tank hasn't been filled or pressurized yet. And so what happens when you drop this pump in a well for the first time, as it powers up and it starts to pressurize that line going up to the pressure tank, and it starts to put water in that pressure tank. And as it does that, it starts to compress the air in there. It's only then that you get some head pressure back against that pump, because without that head pressure, I want to tell you something, all those impellers and diffusers inside that pump end, when that pump first powers up, wants to travel right out the top of that discharge right along with the water. And it's basically because there's no head or back pressure against that pump. Now, once you hook this up to a pressure tank and you pressurize that tank, from that point forward, now every time that pump comes on, it's going to be pumping against at least some pressure. The image that I have down there also occurs sometimes when water well drillers develop wells. Water well contractors use a variety of ways to develop wells. I've seen this firsthand as I've had the privilege of traveling this country for so many years. Some contractors use air. In other words, once they drill the well, they'll pump air down in there to bring all that shavings and all that drilling fluid and mud up out of the top of that casing. They don't want to send that into the house. And so this water coming up out of the top of that casing at that time is horrible looking, terrible looking. And they'll leave that run, open discharge like you see down there until that water clears up. Then they'll hook it on up to the pressure tank and let it come into the house. But that whole time that they're running open discharge like you see here, you will be in upthrust. So you would like to make sure that you've got a bearing system or a washer in there capable of taking that bit of abuse that it's going to see on an initial installation. All right. We come back to here. Is the pump running? Yes or no? Is the pump I'm sorry. Is the pump running? The answer is no. The pump's not running. Okay. That was one of the first questions, and we talked about this initially. I'm going to go to the motor side of this now. All right. I'm going to go to the motor side of this. The motor's not running. So some things to check if the motor's not running. I'm looking at the clock. I'm at about 17 minutes, so I'm hoping to get through the rest of these slides before that time comes up. Obviously, the first thing and the easy thing to do is that if the motor's not running, we want to make sure we got power going to the motor. If there's a circuit breaker or a fuse that's blown, obviously that's the reason the motor's not running. Now, there may be a reason, and there probably is, for that fact that circuit breaker blew or that fuse blew. It's always recommended that you use a dedicated breaker for your well pump, just like you do an air conditioner or a range. You know, a lot of these appliances will have dedicated breakers. It's also important that you put it on a breaker that has the amp rating to handle the amp load. If either of these are if we cut corners on either of these, we could get nuisance tripping of the breaker. In fact, if you do get tripping of the breaker, and every time the pump fires up, it blows the breaker, here's one thing to check. If it blows the breaker, I'd say, also check for the correct voltage to the motor, because incorrect voltage to the motor will also cause a nuisance tripping of these breakers. And also defective drop cable, right? So if you've got a drop cable that's got a pits in it, or the insulation is worn thin, that it'll short out, right? So the problem could be, say from the pressure switch down to the motor itself in the form of that drop cable. So if the motor's not running, we can, with a multimeter, there's any number of things that we can determine just with a simple multimeter, all right? We can determine if a motor is grounded, if it has shorts, if it's got open winding or mixed leads. When it comes to multimeters, there's a couple of choices out there still to this day. Analog, which is what you see on the screen there. If you do happen to use an analog meter, don't forget that you have an adjustment scale down at the bottom that you need to set prior to taking any of your measurements. And then there's also a dial up in the center of that thing so that you can calibrate that each time you use it. In other words, you're going to zero that meter out with that dial up there. The digitals, they have auto ranging features. There's no need to zero them out each time. They are popular with the day and age that we live in today anyway. So either one, it doesn't matter whether it's a digital or an analog. I always tell contractors, make sure the thing's functional. One way you can do that is power your meter up and then take your red and black probes and cross them, just like you see in the image there. When you do that, you should get a reading of what's referred to as infinity. And again, it depends a little bit on the meter itself, but infinity can be displayed one of two ways, either as an OL or simply as a 1. That is an indication of what we call infinity. So this is a no-brainer here, but I can't fail to bring it up. Make sure there is no power to the motor, as we're going to do some tests to determine what's wrong with the motor. All right, so here we go. 2-wire motors, right? There's when it comes to submersible pumps, we got 2-wire motors, we got 3-wire motors. A 2-wire motor is simply going to have 2 black leads off of it and a green ground. So we can refer to those as perhaps lead A, lead B, and of course the green ground. On the 3-wire motor side, you've got the green ground, but you're also going to have a yellow wire, which is a common. Your black wire is going to be your run winding, and your red wire is your start winding. And so, again, understanding these colored cables and what each one of them contribute goes a long way here. All right, so if we want to check for ground, all right, I could do this above. I could do this with the motor in the well too, but basically what I'm doing is I'm going to take my multimeter and I'm going to take each lead to ground. All right, so I'm on a 2-wire motor. I'm going to take each of those black leads, lead A to ground, and then I'm going to check lead B to ground. On the 3-wire motor, I'm going to do exactly the same thing, whereas I'm going to bring my yellow, my black, and my red all over to ground, and I'm going to take a reading of that. All right, and here this is pretty black and white. if there's no resistance, in other words, I'm still showing infinity in my meter, there's no resistance, I'll tell you that there's no ground. That's black and white. I'm not telling you the motor's good. I am telling you that it's not grounded. Okay, so if there's no resistance, there's no ground. On the other hand, if you get any resistance, even small amounts, any resistance at all will indicate a ground. So that's a pretty black and white test to be able to run with a multimeter for the simple purpose of determining whether you're grounded, got a motor that's grounded or not, right? I had a guy come up to me one day at a trade show, and I was doing a class on multimeters, and he said, Mr. Painter, he said, I pulled a pump out of the well this week, and he said, that rascal was grounded on all three legs. He said that as though that surprised him. He said that like, that's really grounded, man. I mean, it was on all three legs. Well, the truth of the matter is, in most cases, if you get resistance on any lead, you'll probably get them on all. I mean, that's more the rule, actually, rather than the exception. And there'll be a day, hopefully, I don't know if it's going to be in my lifetime, but I would think that by now I wouldn't even have to bring this up anymore. But, you know, the very first submersible pumps that were manufactured back in the 60s, early 70s, they didn't have a ground wire on them. So when you pulled the pump out of the well, it didn't have that green ground. You, the installer, you had to figure out how to ground that water system. So if you happen to pull one of those motors out, we can still test it for ground, but we've got to create a ground since it doesn't have a wire. And so, you know, if it's a steel cased well, you can rub that probe along that casing, get a good solid, you know, contact, and you can use that as the ground. If you happen to have the pump and motor out of the well, you can, again, on the side of that motor shell, that stainless steel, you can create a nice ground there, and you can determine whether the motor is grounded or not. So up here at the top, again, if we're going to check for a ground, we go lead to ground, each lead to ground. If there's no resistance, the motor is not grounded. If there's any resistance at all, that indicates the motor is grounded. Okay? Now, that's the only time we're going to use the ground wire. That's it. From now on, we're going to measure everything else lead to lead, whether we're looking for shorts, whether we're looking for open windings, or whether we're looking for this thing called mixed leads. We're always going to check lead to lead. And in so doing, our meter is going to give us some kind of a value, all right? It's going to give us a value. And sometimes we think, okay, well, what should those values be? Well, we publish what's called a motor application guide. And by the way, folks, I have attached this to the dashboard of your, I've attached this. If you look at your dashboard and you scroll down, you'll see these tabs. One says handout. I've got a couple of handouts that I've attached, and this is one of them, this motor application guide. So when we're done here this afternoon, I'm going to leave this up for a while in case you may want to download these PDFs that I've attached. But inside this motor application guide is those values that we're looking for, all right? So let's look at this. There's a column on the far left-hand side. There's your difference between the 2-wire and your 3-wire motors. So we need, you know, if I'm going to do a test, and I need to determine, am I doing it on a 2-wire or a 3-wire? The next column over is the horsepower, right? So make your selection on the motor that you're going to test. If you scroll across that table, you'll come over to this column called winding resistance. There's your values, all right? So they're published. They're published values. And so, again, if we look at let's just take a 3-wire pump. Let's say it was a 1.5 horses, all right? It was a 1.5 horses. I'm just kind of using this as a virtual whatever here. So if I come across from that 1.5 horses 3-wire pump, I'm getting 2 sets of values over there. I'm getting a M value of 1.7 to 2.2, and I'm getting an A value of 7.8 to 9.6. Now again, this is on a 3-wire motor. So if I want to know what that M and that A is, if I just drop down to the bottom of that chart, it's going to tell me. My yellow to black, that's my M value. That's 1.7 to 2.2, and the yellow to red is my A. That's 7.8 to 9.6. If you've been checking, if you're checking a 2-wire motor, well, you got one set of values. You're going to go black to black, right? We're going to go lead to lead. We've done it one time, black to black. So you only have one set of values there. But nonetheless, these values are published. So when we look at these values, all right, looking at these values, the yellow and black, which was that M value, we can refer to that as the lowest value. I'm going to have to move my dashboard briefly. Yep, lowest value. Come down to the next one, the yellow and the red, which is your common and start windings. That's your A value, that's the values under the A. That's what we would call intermediate value. And then if you put your probes on the start and run windings together, the red and black wires, that's going to be the highest value. Even though we only published the two values, we'll have three of them over here, right? So let me walk you through that scenario real quick. Let's see if I can get this slide to change here. There you go. All right. So we've got the low value and the intermediate value. And the question is, okay, if you're telling me what those two should be, why aren't you telling me what that last one should be? Well, it's a question mark. We'd only publish those two. I'll tell you how you can determine that. It's very easy. You take the lowest value, add it to the intermediate value, and that ought to give you some idea as to what that high value should be. All right, so it's pretty much a basic math equation here. And I'm not saying you have to be absolutely spot on. In other words, if the low value was 2 and the intermediate value was 8, meaning the highest value be 10, that's what we just said. Well, what if it's 10.1? Hey, it makes sense to me, all right? Close enough. So it just needs to make sense. So again, if we were to take this 1.5 horse 3-wire motor and we were going to run a test on it, okay? So the very first thing I'm going to do is I'm going to put my probes on the yellow and black wire, and I get a reading in my meter, and it's 1.8. Well, when I look over here at the range, it's within range, right? 1.7 to 2.2, so I'd give that one a good grade. Now I'm going to come down and do my, and by the way, if you come through this whole exercise and everything's in range, well, that's probably an indication of a good motor. But we're talking about troubleshooting bad motors here. So now I'm coming down to this next one, and I put my probes on my yellow and my red. And now I'm coming in, well, that's not good. I'm coming in at 1.7. So it's below the range. It should be 7.8 to 9.6. Now I'm going to tell you something. Any time one of these top two, yellow and black or yellow and red, anytime one of those top two fail, you might as well just end your test there, because the third one will always fail. Always, always, okay? But let's look at what failed up here. That yellow and black failed. And actually, if we look at that yellow and black, we're coming in, we're coming in lower than published values, right? Lower than published values. All right, so this is how I try to teach young people, even coming into our factory here on multimeter use. When the resistance values are lower than the published values or than the specified values, think of it this way. If it's lower, it's shorter. So lower means a short, right? If you want to shorten the grass, you better lower the motor. So anytime you have resistance values coming in lower than specified, it will always indicate a short, always. And so when we look at this chart, again, that lower than specified is going to indicate a short. In the previous slide, or in this slide, the bottom two failed, right? The bottom two failed, actually. The yellow and red failed, and the red and black, I told you every time one of the above fails, that one always fails. But look at the commonality between the red check marks. Yellow and black are fine if they're together. It's only when we add the red wire to them they fail. And so more than likely, that short will be in the start winding, the red wire. All right, more than likely. Okay, moving to the next one here. We come in, we're going to do another test here. Now this time, if you look, I put my probes on my yellow and black, and I end up with 8 ohms over here. 8 ohms. Well, that's not within range, right? In this case, it's coming in higher than specified. So, they're come down to the next yellow and red, and that's coming in at 9.4. Well, hey, that's right in within range. So I failed on the top one this time. I failed on the top one, and I come in higher. What I'm about to tell you would not matter whether I failed on the top one or I failed in the middle one. The key is here. Anytime the resistance values are coming in higher than specified, higher, all right? How do we equate to what that is? Well, I thought about this for a while. I'm going to admit it's rather corny, but I remember it this way. If I want to think of something that's higher, I walk outside and look up. That's pretty daggone high. What am I looking at? I'm looking at a wide open sky is what I'm looking at. And so anytime we get resistance values that are higher than the specified values, think of that open sky, right? Because if they're higher, that's going to indicate an open winding. And again, when we look at these two that fail, there's a fly in the ointment here, right? The yellow and the red worked good when they were together, throw that black run winding in, and it failed. So more than likely, that open winding is going to be in the run winding because, again, this is what my meter's telling me here. All right, almost through this. So this one's within specs. We're good. If it comes in higher, it's an open winding. This is the last of the tests we're going to perform here, and this is also probably one of the rarest occurrences. But if you look, I just put my probes on my yellow and black. I've got that 8 ohms up there. That's higher. That's no good. I come in. I'm going to drop down to the next. I'm going to go do the common and start winding, and I put my ohm meter on there. That's lower, right? So now I'm coming in higher and coming in lower. That's no good. And again, by this point, you don't need to do anything with that start and run winding. The problem's already showed itself. And the problem here is that anytime you have readings that are coming in both higher and lower, that is an indication of what is called mixed leads, all right? And again, this is not a very common occurrence. It's the rarest of all of them, but it happens. It can happen, and it's you ask, okay, well, what are you talking about, mixed leads? I suppose that when the manufacturer puts the lead socket in the motor and they wire the bottom side of that, if they didn't wire that properly, and now you put your motor lead down on top of that, you're not lined up. Your red wire's not lined up to the internal red or the internal yellow. They're off one. Who knows? They're not the same. This could not happen at F&W. There's way too many tests that would red flag that thing way, way, way early on in the manufacturing process. And I'm not saying that somebody else is capable of doing it, but we're all human beings. And so, it's a possibility, albeit rare, that somebody didn't get that lead socket in properly. More than likely where that's going to occur is in the splice, right? In the splice where we didn't put the wires back the way they were supposed to be. And, sometimes these wires, they get old, the color fades. You can't tell one color from another. Although with my multimeter, I could tell you what every one of those wire colors are. If they were all black, I could tell you which one should have been red and which one should have been yellow, because I know which two are the lowest values, I know which two are the intermediate, and I know which two are the highest. And so, again, when you come in and you're within higher and lower, that's always going to be an indication of mixed leads. So a couple takeaways, and I'm going to close this off. I see I'm at 3 o'clock. A couple of takeaways. Anytime you put a test on a motor or drop cable and a motor, and you're coming in within specified range, that's always good. That's always a good thing. However, if you are coming in lower than that specified range, that's going to indicate a short. If you're coming in higher than that specified range, that's going to indicate an open winding. And as we just talked about, if you're coming in both ways, you're mixed up. You got mixed leads, right? Mixed leads. So hopefully that little chart right there will be a good takeaway for you. And the other is to know that if you take your lowest value and you add it to your intermediate value, it ought to give you some idea of where that highest value should be. So again, this is what I just have on the screen now. And I don't care whose motor it is that you're testing. It can be Flint & Walling. It can be any other brand that's out there. This holds true. This holds true. So I think with that, again, that motor application guide is attached to the handout there. Feel free to download these. Again, I'm going to leave this screen up for just a bit. And with that, I'm going to go ahead and close this out. And I appreciate you joining me today. But with that, thank you. The training has now concluded.